I will be walking you through the second paper, Exploring Physics for OCR Physics A in the exam series of June 2024. Let's get started with section A. We've been asked to work out the base units of kilowatt hour. Kilowatt hour is the unit for energy. Energy can be written as kilograms meter squared per second squared. So C is the answer. Question 2. A neutrino is a fundamental particle. First things, it's a lepton and interacts through weak nuclear interaction. So D is the answer. Question 3. Which of these non-invasive medical scans does not expose the patient to ionizing radiation? C is the answer. Question number 4. Given 3 capacitors arranged in circuit, calculate the total capacitance between X and Y. Given these 2 capacitors are in series, their capacitance will be calculated by the formula of 1 over C equals 1 over C1 plus 1 over C2, or quite simply, C is equal to C1 times C2 over C1 plus C2. So that would be 0.33 times 0.22 over 0.33 plus 0.22. So that would be the 2 together. Then this is in parallel with the sum of the 2. Added up to the answer, we just have to keep it in terms of microfarad. Once you put that in the calculator, you will get 0.6, which is B. Question number 5. The image shows a micrometer being used to measure the diameter of a wire, and it has a zero error of 0.07 millimeters. The measured value is 2.88 millimeters. Because it has a zero error of 0.07, take it away from 2.88. Okay, this is the diameter. Convert it into meters, so times it by 10 to the minus 3, square the answer and use it in pi r squared, and I got B as the answer for that. Question number 6. The image shows an oscilloscope measuring alternating voltage. The time base is 0.1 seconds per division, and the voltage scale is 0.5 volts. We need to work out amplitude and frequency. The amplitude is the height from the resting position, so that's 1, 2, 3, and 3.5. So 3.5 times by 0.5, which is 1.75. In terms of the frequency, it is going to be from this point to this point, which has 4 times by 0.1, which is 0.4 seconds, to calculate the frequency. So that will be 1 over 0.4, and therefore we would get B as our answer. Okay, question number 7. This is about the rate of decay of a radioactive source. The rate of decay is dependent on the rate constant. Yes, true. Independent of the mass of the source. Incorrect. Depends on the time, of course. So that is going to be B, which is the option, with 1 and 3 being correct. Question number 8. A student is using a spreadsheet to model the decay of a charge on a capacitor. They're using this equation. The student chooses a time interval of 0.5 seconds, and at t equals 0, the charge on the capacitor is 600 microcoulombs. So what is the charge at t equals 1.5 seconds? So we would have to work our way up to it. And for delta Q, it's 480 times delta T, which is 0.5, divided by 2.5, and that would be 96 microcoulombs. 480 minus 96 will give me 384. use that again in my calculation. 384 times 0.5 over 2.5, and I would get 76.8. And again, I would get 307.2. So D is the answer. Let's move on to question number 9. The diagram shows a string stretched between two posts, and we need to work out the phase difference between P and Q. So we've been given stationary wave. And one thing we need to know is between 2 points, it can only be in phase or out of phase, either 0 or pi. Okay, so either A or D. Now, in order to understand this further, a couple of things I guess you shouldn't know, you should remember, is that if you have odd number of nodes between the 2 points concerned, then it's in antiphase. If you have an even number of nodes, it will be in phase. So over here we have 2 nodes between points P and Q, and therefore it would be in phase, and answer will be A. All right, so I hope that makes sense. Do remember that because it comes up quite often in the exam. Nodes is antiphase, even number of nodes is in phase. Let's move on to question number 10. A student uses the circuit below to determine the electromotive force and internal resistance of a battery. They measure the current and potential difference across the variable resistor for different resistor values. A graph is drawn between potential difference and current on y and x-axis respectively. Which row is correct for calculating the EMF and the internal resistance of the battery? Compare this with the known equation of EMF, which is EMF is equal to V plus I times R. And because V is EMF minus IR, we can say, we know that the y-intercept is the EMF. And then the gradient will be equal to the internal resistance. So that over here compares to R. So D is the answer here. Question number 11. At the equator of the Earth, the magnetic flux density is approximately 25 microteslas. What is the magnitude of the force on an electron with a velocity of 100 kilometers per second as it is moving perpendicular to the Earth's magnetic field at the equator? So we know F is equal to BQV. 25 times 10 to the minus 6 teslas. Charge on an electron is 1.6 times 10 to the minus 19. And the velocity is 100,000 meters per second. And C is the answer. Question number 12. What is the radius of a carbon nucleus that has 6 protons and 7 neutrons, assuming the average radius of a nucleon is 1.2 femtometers? So we know the formula R equals R naught times A to the power of 1/3, just times these two together, and C is the answer. Question 13. A subatomic particle has a positive charge. What type is it? It can't be an antiproton because that'll be negative. And down quark from your data booklet, you can see it has a charge of minus 1/3 of E. So that's out. Neutrino doesn't have a charge. And that leaves us with positron, which is an antiparticle of an electron. So that would be positive. D is the answer. Question number 14. We've been given 1 kilo ohms of resistor connected in series to a battery made of 3 1.2 volts cells. We have to work out the reading on the ammeter. We are given 3 cells of 1.2 volts. 2 are connected in parallel. 1 is connected in series. The voltage across this will still be 1.2 volts. The total voltage is 2.4 volts. Current is voltage divided by resistance. We will have 2.4 milliamps of current. C is your answer. Question number 15. Which sequence shows the energies below in increasing order of magnitude? Number 1. The change in kinetic energy of an electron accelerated through a potential difference of 1 volt. That is 1 eV, which is in the range of 10 to the minus 19 joules. Kinetic energy of a proton with a velocity of 1000 meters per second. We can work that out using half mv squared. The mass of a proton is of the order of 10 to the minus 27, and that would roughly be estimated at 10 to the minus 21 joules. The energy of an X-ray photon, which has a frequency of this much. E is equal to h times f. Planck's constant is of the order of 10 to the minus 34, and this is 10 to the 17, which roughly estimates to 10 to the minus 17 joules. So your correct sequence in the increasing order will be 2, followed by 1, and then 3. So C is the answer. In question 16, thermistors are components whose resistance varies with temperature. And there are 2 types, NTC, where the resistance decreases with increasing temperature, and PTC, where the resistance is proportional to the temperature. A student is investigating how the resistance of a thermistor varies with temperature by measuring voltage and current. The thermistor is in a water bath, and the temperature of the water is measured using a thermometer. The diagram below shows how the student has set up the experiment, and it's been set up incorrectly. Describe how the student should change the circuit. So this voltmeter over here shouldn't be in series. It should be placed in parallel, and that is because the voltmeter has a very high resistance. It would prevent the current from flowing through the circuit if placed in series. Part B. We've been given the data for the corrected circuit and asked to plot the remaining points on the graph. At 70 degrees Celsius, we have 2.8 milliamps of current. So at 70, 2.8 is going to be here, followed by at 80, 3.66 in the middle somewhere. And then at 90, we have 4.76. We have been asked to draw a suitable line of best fit through the data. This will be a curve, and it will be passing through all the data points. Let's move on to the next one. In part C, we have to describe, using the graph and the calculations using the data from the table, how the resistance of the thermistor varies for increasing temperature, and then determine whether the thermistor is NTC or PTC. So let's go back up, and from the graph we can say that as the temperature is increasing, current over here is increasing as the gradient is getting steeper. From the table, we know that the voltage remains constant, and therefore as the current will increase, the resistance will decrease, and we can prove that by using R is equal to V over I for voltage and current respectively. Make sure you convert this into amps. For instance, 3 over 0.75 times 10 to the minus 3 gives 4,000 or 4 kilo ohms. Similarly, another value gives me a value of 2.72 kilo ohms, which clearly shows that the resistance is decreasing with temperature. So it must be an NTC thermistor. Let's wrap this up. So as temperature increases, current also increases, and resistance decreases. From the data points, it's 4,000 and 2.72 kilo ohms for the next values, and therefore it's an NTC thermistor. Part D. The thermistor is used in a temperature sensing circuit for a heating system to warm up the milk for a baby. We've been given two possible circuit designs. In each circuit, the voltage out is across the thermistor is connected to a heating system to warming up the milk. Discuss which circuit may be suitable for the heating system by considering the response of the circuit to changes in temperature. So in circuit 1, there's only one component. As the temperature increases, the voltage would stay more or less the same because the potential difference is not being shared by another component. In circuit number 2, V out will vary in proportion to the resistances. So V out will decrease when the temperature increases as the resistance decreases. We want the heating system to come on at low temperatures. Therefore, circuit 2 is the answer. Okay, question 17. Diagram shows two loudspeakers X and Y connected to a signal generator. The loudspeakers emit sound waves of the same amplitude and frequency which are in phase. Microphone M is moved along a line from P1 to P3 and the signal is recorded on an oscilloscope. As the microphone is moved along the line P1 to P3, the oscilloscope shows maximum signal at P1, 0 at P2, and the next maximum at P3. Explain these observations. We know that constructive interference is happening at P1 and P3, and destructive interference is happening at P2 due to waves from X and Y meeting in phase and out of phase respectively. Okay, part B. The distance between the centers of X and Y is 70 centimeters, D is 4 meters, and the distance from P1 to P2 is 1.25 meters. Use the two-source interference formula to calculate the frequency of the sound waves. The speed of sound is 340 meters per second. We know lambda is equal to AX over D. And A is 70 centimeters, which is 0.7, times X, which is from the maximum to a minimum. We must double this value to get the distance between the two bright fringes, 1.25 times by 2, divided by the distance of 4 meters, and that would give me 0.4375 meters. From here, I can work out that frequency is speed, which is 340, divided by the wavelength of 0.4375, and that gives me 780 to two significant figures. Part C. The loudspeaker Y is now replaced with a loudspeaker that produces sound waves of twice the amplitude. Describe how the signal observed on the oscilloscope varies as the microphone is moved along the line P1 to P3. Since X still has the same amplitude, when the signal interferes with Y now at P2, it won't be destructive interference anymore. So there would be some signal observed as the waves will meet somewhat in phase rather than completely out of phase. Part D. For I, it says explain what is meant by the term intensity. It's just the radiant power per unit area. In part II, it says calculate the factor by which the intensity of the sound waves at P1 in part C is larger than the intensity of the original sound at P1, sound waves at P1. Intensity is directly proportional to the amplitude square. So let's go up and let's say that originally from X and Y, the amplitude is, let's say, A. The total amplitude is 2A. The amplitude from Y has increased to twice as much. It's going to be higher, 2A. The total amplitude will be 3A. If we set up a ratio for the intensity, total amplitude is 2A, and the new total amplitude is going to be 3A. Now that the intensity relationship is directly proportional to A squared, we can simply do the new intensity over the old intensity, 3A over 2A squared, which gives us 9A squared over 4A squared, and therefore the ratio becomes 9 to 4. So that's a really good question. In question 18, it says, describe an experiment to determine the output current of a step-up transformer depends on the number of turns on the secondary coil, and explain how the data can be analyzed to establish the relationship between the output current and the number of turns on the secondary coil. We have been provided with the wire and a suitable core on which to wind the wire, as well as any other normal lab equipment. Use the space below to draw a labeled circuit diagram. Okay, so let's get the diagram up. I've got a step-up transformer, and in this step-up transformer, I've got the input current IP with the number of primary turns, and the secondary wire with the number of turns as NS and the current being S. So we have to work on finding a relationship between the output current and the number of turns in the secondary coil NS. Let's start with the formula first. NS over NP is equal to IP over IS. This has been given to us. If I rearrange this formula, I would end up getting NS times IS equals IP times NP. We want to establish a relationship between NS and IS. Keep the initial current and the number of turns in the primary wire constant. If these are constant, then NS is equal to the constant divided by IS. The number of turns in the secondary coil is inversely proportional to the output current. We can prove this relationship by collecting appropriate data. We don't have to worry about how the data is collected, just how it can be analyzed. Ideally, you would increase the number of turns in the secondary coil, which will, at a given time, okay, so you measure the current, increase the number of turns in the secondary coil, measure the current again, and so on. You would notice a decrease in the output current. One can plot a graph of NS versus 1 over IS or IS versus 1 over NS. They would observe a straight line passing through the origin, something along the lines of this, basically. Part B. A simple laminated iron core transformer takes mains voltage of 230 volts and 50 Hz into a primary coil. The output voltage from a secondary coil is 5 volt and the primary coil has 920 turns. we're given Vp and Vs and Np. State Faraday's law. EMF is directly proportional to the rate of change in magnetic flux linkage. In part II, show the number of turns in the secondary coil is 20. We know Ns over Np is Vs over Vp. Therefore, Ns is equal to Np times by Vs over Vp, which is 20. Next part. At a particular instant, the output voltage from the transformer is 3.4 volts. Calculate the change in magnetic flux experienced by the secondary coil in a short interval of 1.2 milliseconds and state its unit. Assume the output voltage from the transformer remains constant at 3.4 volts, so EMF is equal to N times delta phi over delta T. And we are working out delta phi. So let's rearrange. Delta phi is equal to EMF times delta T over the number of turns. Given the output voltage is 3.4 times the change in time, 1.2 milliseconds, divided by the number of turns in the secondary coil, which is 20. That ends up giving us a value of 2 times 10 to the minus 4 Webers. Let's move on to question 19. In this diagram, we have been shown part of an X-ray telescope which uses a crystal scintillation device to detect low-energy X-ray photons from the star. And X-rays hit the crystal and cause it to emit visible light photons. These travel to the photocathode in an evacuated tube. The photocathode uses the light photons to produce electrons. Each X-ray photon detected by the telescope has 32 kilo eV of energy, and the light photons have a wavelength of 510 nanometers, with the efficiency of the crystal being 15%. We have to show that each X-ray photon produces about 2000 light photons. The light photons each have a wavelength of 510 nanometers. So we can work out the energy of each of these light photons, which is given by hc over lambda. Each X-ray photon detected by the telescope has an energy of 32 kilo electron volts, but only 15% is actually accepted by the crystal because the efficiency is 15%. In order to work out the number of these light photons produced, we need to work out how much energy there is of these light photons. So that should be worked out in joules and then convert this into joules or electron volts as well. So that's quite simple, and you just have to use these values in the calculator. I'm going to get that in EV, so 510 nanometers. So all that must be divided by 1.6 times 10 to the minus 19 joules. That gives me a value of 2.4375 electron volts. And only 15% efficiency is about 4800 electron volts. Therefore, in order to work out the number of light photons produced, knowing that it's one-to-one interaction, it will be 4800 electron volts divided by the energy of each of these light photons, which is 2.4375 eV. That gives me 1969 number of photons, and that rounds up to 2000 light photons. So I hope that makes sense. Part B, the photocathode has a work function of 2.3 eV. Work function is the minimum energy required by the metal to release a photoelectron from its surface. Part II, we need to calculate the maximum kinetic energy of the photons leaving the photocathode. So we know the photoelectric equation as HF equals phi plus EK max, and therefore EK max will be HF minus phi, and we've been given the value of work function, which is 2.3 eV, and the energy of the photons is 2.4375 eV. So therefore we can take them away and end up getting a value of 0.1375 eV, which must be converted into joules, so times it by 1.6 times 10 to the minus 19, and that gives me an answer of 2.2 times 10 to the minus 19 joules. Next part, 12 X-ray photons are detected every minute. Use your answer to part A to calculate the current leaving the photocathode. Assume all photons produce photoelectrons. 12 X-ray photons, which means that 12 times 1969 light photons are produced, and that times by the charge on the electrons, which is 1.6 times 10 to the minus 19 coulombs, and divide this by 60 seconds. So all that divided by 60 seconds gives me a value of 6.3 times 10 to the minus 17 amps. State one other assumption to calculate the current. It's basically one-to-one interaction. That is that one electron is absorbing the energy from one photon. All right. The diagram below shows the average nuclear binding energy per nucleon for a number of different isotopes. Explain the nuclear binding energy of a nucleus. It's the energy required to separate the nucleons, protons, and neutrons. Part B, suggest why isotope H1 of hydrogen has not been included on the diagram above. That's because the nuclear binding energy is 0, because it's got only one proton and no neutron. Part C, the main nuclear fusion reaction in the Sun is between deuterium and tritium. This reaction can be written as shown below. Explain why isotopes with low mass numbers, such as hydrogen, undergo nuclear fusion. They are less stable than heavier ones. So the more binding energy per nucleon, the more stable they are. Use the diagram at the start of this question to show that for the reaction of deuterium and tritium, the energy released in each fusion event is approximately 3 times 10 to the minus 12 joules. Okay, so let's just have a look at the diagram. For the value of deuterium and the value of tritium, that's about somewhere between 2.8 MeV, and the heavy hydrogen is about 1.1 MeV. So that's that. Okay, we'll put that into calculation. So if you want to calculate the the energy released, it is essentially the binding energy times the nucleon number. And the change in energy, or the energy released, is 1.1 MeV. We'll convert that all at once into joules, times by the number of nucleons, which is 2 for deuterium. Then we have 2.8 times 3, which is the nucleon number of tritium. So all that minus the products now, which is helium. Helium has about 7.1 MeV per nucleon and 4 nucleons. So 7.1 times 4, all times 1.6 times 10 to the minus 13 joules, as it's in MeV. That ends up giving us a value of 2.85 times 10 to the minus 12 joules, or as they say, 3 times 10 to the minus 12 joules. Next part, the sun's mass decreases by 4.3 times 10 to the 9 kilograms every second. Assume the mass loss is due to this reaction. Calculate fusion events per second occurring in the sun. So delta E is equal to delta M C square, where delta M is the mass defect. We have 4.3 times 10 to the 9 kilograms per second times the speed of light squared. That would give me a value of 3.87 times 10 to the 26 joules per second. In order to find out the number of fusion events, we know that each fusion releases this much amount of energy. So all we got to do is divide our number by 2.85 times 10 to the minus 12. That would give me 1.4 times 10 to the 38 fusions per second. In part D, in the sun, deuterium is produced from fusion of 2 hydrogen nuclei, and there is a missing particle. Determine the charge on the missing particle. We know that the total charge here is plus 2, and the charge here is also plus 2. Therefore, the missing charge must be 0, as the charge has to be conserved. The missing particle is a lepton, so the total, it adds up to 2 over here, and over here as well it adds up to 2. That's an easy one. This is going to be an electron neutrino. This is something you should remember, that with a beta positive decay you end up getting electron neutrino, and with a beta negative decay you end up getting the anti-neutrino for the electron. In the next one, it says, in the fusion reaction above, determine the total number of up quarks at the start of the reaction. Let's see. At the start we have 2 protons. A proton has a quark composition of UUD, so there will be 2 U quarks per proton. Therefore, there will be 4 up quarks at the start because there are 2 protons. Part E. Tritium is another isotope of hydrogen which is formed in stars. On the Earth, tritium is a radioactive element which decays by beta negative emission. Write down an equation in terms of the quarks. Okay, in terms of the quarks, we know that beta negative happens when a down quark turns into an up quark. So that is as simple as knowing and incorporating, obviously, the anti-electron neutrino here. All right, question number 21. We have been given that technetium 99M is a metastable isotope, radioisotope, which can be used as a tracer in medical diagnosis. It is injected into the body and decays by gamma emission into technetium 99 according to the chemical equation. Explain what is meant by a tracer. It's a substance used to detect activity in the body. Part II. Technetium 99M only emits gamma radiation. Give 2 advantages of using a tracer which only emits gamma radiation. Gamma radiation is least ionizing, and secondly, it's most penetrating, so it's easy to pass through the body tissues. Part B. A technetium 99M tracer with an activity of 900 megabecquerels is injected into a body. The half-life is 6.01 hours. Calculate the number of technetium 99M nuclei initially present in the tracer. We know that N is equal to N naught e to the minus lambda t. I'm going to work out the value of lambda. And we know it's asking for initial, right? So this is when t is 0. When t is 0, n is the same as n naught. I need to work out n, and I know lambda is equal to ln 2 over the half-life, which is 6.01 hours, and obviously convert it into seconds. So that would be 60 minutes and 60 seconds, and that gives me a value of 3.2 times 10 to the minus 5 per second. I know n is equal to the activity, 900 times by 10 to the 6 becquerels, divided by 3.2 times 10 to the minus 5, as I know that n is equal to a over lambda. Okay, so that is going to give me an answer of 2.8 times 10 to the 13. All right, part II, we need to calculate the time in hours taken for the activity of the tracer to have fallen to 3% of its initial activity. So activity is 3% of initial. We need to find out the time. A is equal to A naught E to the minus lambda T. So I know that it's 0.03 of A naught is equal to A, E to the minus lambda. Rearrange ln of 0.03 equals minus lambda T. Divide the value of ln 0.03 by negative lambda, which was 3.2 times 10 to the minus 5 per second, and that gives me a value in seconds, and I need to convert that into hours, so that can give me an answer of 30 hours. Okay, so that's part B done. Let's move on to part C. The daughter nucleus decay by beta emission with a half-life of a little over 200,000 years. Approximately 50% is stored in the bones and 50% is passed out. Suggests why the presence of this remaining technetium 99 in the body causes little additional risk to the patient. The half-life being very long indicates the activity is very low over the average lifetime of a human being. Part D. The half-life of a different radioisotope is to be determined using suitable apparatus. Each count represents one decay. The number of counts is measured for 1 minute every hour over 6 hours. A graph of the corrected count rate per minute against time is plotted and shown. We need to describe an appropriate method that could be used to obtain this data, naming any apparatus and the safety measurements taken, and then use the graph to determine the half-life of this radioisotope, showing clear working out. We need to measure the background count rate without any source present using GM tube encounter at the location of the experiment. Number 2 is we have to take an average of 3 readings, 1 minute each, using a stopwatch, and then subtract the background count rate from this value to obtain the corrected count rate. We are going to repeat these measurements every hour at the same time interval. In terms of safety precautions, we should use tongs to handle the source, keeping as much distance from the source as possible, and use a lead-lined container to store the source when it's not in use, and always make sure you keep the source facing away from you during experiments. The gradient is the change in y-axis over the change in x-axis, and that gives me a value of 8.33 times 10 to the minus 4. When incorporated into my formula of ln 2 over 8.33 times 10 to the minus 4, I end up getting 831.77 or 830 minutes as rounded to two significant figures. In terms of the calculations, I would begin by talking about the equation. We know that A is equal to A naught times e to the power of minus lambda t. And as per this graph, we know that if we take natural log of both sides, ln A is equal to ln A naught minus lambda t. Now, comparing this with the equation of a straight line, we know y equals mx plus c, so m is the gradient of this graph. Let's calculate the gradient. Use 7.805 and a triangle will be 7.505. So my gradient would be 7.805 minus 7.505 divided by the time over 6 hours, and make sure you convert it into minutes. So times it by 60, and that gives me a value of 8.33 times 10 to the minus 4. Lambda is related to half ln 2 over half-life. Half-life can be calculated by using ln 2 over the gradient. So it would be ln 2 over 8.33 times 10 to the minus 4, which gives me 831.77, which is 830 minutes. That would be my answer. This question is about lightning. Part A, sheet lightning occurs when there is an electrical discharge between the upper and the lower regions of it. The upper regions are positive and the lower regions are negative, modeled as an ideal parallel plate capacitor with circular horizontal plates. We have been given a bunch of data values. For part I, we have to draw on the diagram the electric field lines between the capacitor plates. So that's an easy one. We know this is positive and this is negative, so the field lines are from positive to negative, lots of parallel, equally spaced lines, and that will be part I sorted. So let's move on to the next part where it says, suggest why the actual electric field lines would differ from what you have drawn. That's because the cloud doesn't have a flat or parallel surface like a plate. It says, show that the potential difference V between the plates is about 1 times 10 to the 9 volts. So that's an easy one. We know V is equal to electric field strength times the distance between the plates. Electric field strength is given to us as 4 times 10 to the 5. The distance between the two plates is 3.2 kilometers, so 3.2 times 1,000. And that gives me 1.28 times 10 to the 9 volts. Okay, then the next part says calculate the capacitance C of the model capacitor, assuming the permittivity of the material of the cloud is the same as the permittivity of free space. C is therefore epsilon naught times A over D. The value of epsilon naught is in the formula booklet. Work out the area, which is pi r squared. The diameter was given as 24 kilometers, so that will be 12 times 10 to the 3 squared as the radius over the distance, which is 3.2 times 10 to the 3 meters. Part V. Calculate the magnitude of the charge Q on one of the plates of the model capacitor. we know that Q equals C times V, and we know the values. So 1.25 times 10 to the minus 6 multiplied by 1.28 times 10 to the 9. And that gives me 1,600 coulombs of charge. Fork lightning is an electrical discharge between the bottom of the cloud and the surface of the Earth. Another cloud has a charge of 155 coulombs and is at a height of 2 kilometers. The surface of the Earth has an electrical potential of 0 volts. Assume the cloud acts as a point charge. Calculate the magnitude of the electrical potential between the cloud and the surface. We know V equals Q over 4 pi epsilon naught R, where R is 2 kilometers and the charge is provided. We've been given all the information, so we can just use our calculators to work this one out, and that gives a value of 6.96, or just 7 times 10 to the 8 volts. The lightning strike has a duration of 25 milliseconds, and the cloud discharges at constant rate. That's important because it's not exponential, and the cloud is uncharged after the strike. We need to calculate the number of electrons reaching the ground in 1 milliseconds. Okay, we know that current is equal to Q over T. And we know that there's a charge of 155 coulombs on the cloud, which is discharged at a constant rate, and the duration is 25 milliseconds. So I'm just going to keep it as 25 milliseconds. The answer should be in milliseconds. So that would be 6.2. So it would be coulombs per millisecond, if I may write it down like this. Then, of course, you can calculate this in seconds as well as in amps, but I'll leave it like that. Q is equal to NE, right? If we reuse this equation, I is NE over T, we'll get N as I times T over E. The current is 6.2 in milliseconds times 1 millisecond divided by the charge 1.6 times 10 to the minus 19 coulombs. That gives me a value to two significant figures as 3.9 times 10 to the 19 electrons. That's the end of the paper. I hope you found this useful. See you in the next video. Thanks for watching.